All right, we're back, and we have phenomenal news. We found them. They were stuffed away in some book. But we're gonna just talk through this one. Pathways aerobic respiration. So this is in the presence of oxygen. Green stars mean mitochondria. That's where they happen. But first step is gonna be glycolysis, tried and true. Glucose, and you use 2 ATP. Gives you 2 pyruvate, 4 ATP total, net 2, and then 2 NADH. The enzymes we're concerned with are going to be, let's use red, hexokinase, pyruvate kinase, phosphofructokinase, which is also going to be the rate limiting enzyme. That's what that stands for. These are all kinases, so they're all going to involve the addition of a phosphate group, or the inclusion. They're going to do something with a phosphate. That's what kinase means. Hexokinase, first step, glucose 6 phosphate, pretty simple. Uses the ATP. And then we have pyruvate kinase. That's going to do phosphoenolpyruvate 2 pyruvate, the final step. First, last. And then the rate limiting step is going to be fructose 6 phosphate to fructose 1,6 bisphosphate. The positive regulators are going to be AMP, because we want glucose or glycolysis to go when we're low on energy. Negative regulated by ATP and citrate. Then we're going to take the pyruvate from here, and we're going to go right up into the pyruvate dehydrogenase PDC dehydrogenase complex. Pretty much we're going to turn it to acetyl-CoA and one more NADH, and then we're going to take this acetyl-CoA, plop it right on there, and from here on out we're in the mitochondria. We're going to take the acetyl-CoA, add it to oxaloacetate, and then from that 6 carbon molecule we're going to bring it back all the way down to 4 to regenerate that oxaloacetate. And in the process we're going to make 3 NADH. There shouldn't be a 2 there. 1 FADH2, and then 3 carbon dioxides. I feel like we make a GTP here too. I don't know why I didn't include that. And then special little note here, we're going to share complex 2, succinate dehydrogenase, with the electron transport chain. The rate limiting enzyme for this is going to be isocitrate dehydrogenase. It's going to be an oxidative decarboxylation. So what we're going to do is we're going to make one of these CO2s, and then we're going to make an NADH2, and we're going to take out a carbon. So we're going to go from isocitrate to alpha-ketoglutarate, and we're going to make an NADH in this process. It's going to be positively regulated by ADP, and then negatively regulated by ATP and NADH. Then, with all of these NADHs, right, DHs and the FADH2, right, we're going to go through a series of redox reactions with increasing reduction potential, with oxygen being final electron acceptor, final E- acceptor, and pretty much that NADH is going to go from PDC and Krebs, right? DH is going to come here, and then it's going to become NAD plus again, right? And that's going to go to compound or complex 1. And then complex 2 is where we're going to get the FADH2 from Krebs, and then also the NADH from glycolysis. I don't know where I have that, but this, we're going to go sneak all the way through here, and we're going to go there. And that's why actually in eukaryotes we make 30 ATP, and then prokaryotes get 32, because complex 2, we lose a little bit of the reduction potential. Going through here, transfer less. We have to use a little bit more to get it there, because it doesn't really want to go there. But then complex 1 and 2 are going to transfer over to complex 3. Complex 3 goes to complex 4. These are all proton pumps, so they're just going to be sending H pluses, right, across the membrane, right? And it's just going to be sending H pluses. And then ATP synthase is going to generate ATP from this proton gradient, and NADH is going to make 2.5 ATP, and then per like one molecule, and then FADH2 is going to make 1.5 ATP per molecule. And then yeah, that's that.